Okay, so let's think about that two-site binding situation in a different way. In particular, let's think about it in a more explicitly detailed way, right? So let's draw out our macromolecule here. So let's say we've got our protein that has two binding sites, and I'll represent it just this rectangle. It's kind of split in half, right? And now we're going to say, well, ligand can bind to this site or to this site first, right? Site 1 or site 2. I'm going to use A and B. So if sort of the A site here and the B site here. And to distinguish this derivation from the one we used before, I'm going to use a different symbol. I'm going to use kappa for the dissociation constants here. So I'm going to use this kappa. So this would be binding of a ligand to the A site or the B site with dissociation constant kappa sub A or kappa sub B, right? And in sort of a detailed sense, what that would look like would be, I don't know, protein bound to the A site, all right? We'll just mark it this way. Or the protein bound over here to the B site, and we'll just mark it this way, right? Okay. All right, but we're not done, right? We can always bind the ligand to the other site, right? So this would now be kappa B, and completing the cycle, this would be now kappa A, because again, we're assuming that these kappa, these dissociation constants, don't equal each other, right? But we're assuming that they're independent, right? There's no interaction between them. Okay, so that would give us our overall molecule here, now fully liganded, right, with both binding sites occupied. Okay, cool, right? Now, how do we describe that? Well, because the way we've set this up, we can think about the fractional saturation or the degree, the degree of binding to each site independently, right? We can say, well, the total degree of binding here for this model would have to equal the degree of binding for the A site plus the degree of binding for the B site. We kind of did that before when we did that really simple-minded derivation for two-site binding. So in that case, that would look something like this. That would mean I've got to have concentration of our ligand A over kappa A plus the concentration of ligand A plus concentration of A over kappa B plus concentration of A, right? Because each one of those is the degree of binding to each site. They're independent, so we can just sum them. All right, well, that's kind of cool, because if that's the expression, all I got to do is find a common factor, right? And I can just add those things up. When you do that, the degree of binding expression now looks something like this. Kappa A times concentration of A plus kappa B times the concentration of A plus 2 times concentration of A squared. This is just like really basic algebra, so I'm just going to leave it to you guys to remember how to find your common factor and expand this, right? Divided by kappa A times kappa B plus kappa A concentration of A plus kappa B concentration of A plus concentration of A squared. That's our degree of binding expression for this explicit so-called microscopic view of binding. Microscopic because we're looking microscopically, individually at a particular binding site and its associated individual site affinity. That's the degree of binding expression. Well, I can rearrange that, right? I can like make that a little simpler. So let's do that because I've got some common factors there. So let's factor out A up there at the top. That means we can write down something that looks like this: kappa A plus kappa B times concentration of A plus 2 times concentration of A squared divided by kappa A, whoops, kappa B plus kappa A plus kappa B times concentration of A plus concentration of A squared. All right, now here's the thing. Look at that expression, right? And let's compare it to the macroscopic, the final expression we got when we went through that macroscopic binding equation, right? So that one, if you recall, looked like this. It was K2 times the concentration of A plus 2 times concentration of A squared divided by K1 times K2 plus K2 concentration of A plus concentration of A squared. Notice something? Just compare those two expressions. The basic mathematical form of those two expressions are identical. Even though we started from two completely different sets of assumptions in terms of how we were thinking about what's binding where, the form's identical. And look at this. If you think about that constant, this relationship here, those here. What those mean, what the similarity of those forms mean, is that we can define those macroscopic binding constants in terms of these microscopic affinities. And specifically, those relationships say that the macroscopic K2 is simply equal to the sum of those microscopic affinities, kappa A plus kappa B. And because K1 times K2 is equal to Ka times Kb, so because K1, K2 has to equal kappa A times kappa B, because that's true, and because this first expression is true, we can rearrange this expression, substituting in here, and the following must also be true, that K1 has to simply be equal to kappa A times kappa B divided by kappa A plus kappa B. So there's a direct relationship and specific relationship between those microscopic binding constants, which explicitly sort of model the affinity of the individual sites, and that those macroscopic binding constants, right, that come from not thinking about it, right, in that detailed term. There's just one thing bound and then a second thing bound, right? And that relationship is quite is specific and in a really sort of interesting way, right? Like I said, these K1 and K2 terms are often generally referred to as microscopic binding constants. Sorry, macroscopic binding constants. And these kappa terms are referred to then as microscopic binding constants. Right? Okay, so here's the interesting thing. Look what happens if you assume, based on those relationships, if you assume that the microscopic affinities are identical. Assume that kappa A equals kappa B, and we're just therefore going to just call it kappa, that there are two independent sites that have exactly the same affinities. Based upon those two relationships, what has to be true? That's kind of cool. If I just substitute that K in there, that means that K1, remember, kappa in this case is going to just be our microscopic affinity that's shared. It's the same for both sides. If I just substitute that in here, here, and here, the following relationships then have to hold. That K1, that first macroscopic binding constant, has got to be equal to 1/2 kappa, or the microscopic affinity, while the second macroscopic binding constant is equal to 2 times the microscopic affinity. That's cool, right? And if you substitute these back in and go through the solution, you'll ultimately end up finding that the first really simple expression we derived for two binding sites of identical affinities that are non-interacting, you'll come back out with the expression, the generalized expression that I noted before here, right? But sort of more importantly, or more interestingly, these sort of coefficients, that microscopic, true microscopic affinity that compose the macroscopic affinity, these sometimes get a name. These are often known as statistical factors. Right? So if you think about what that means, that first expression for K1 means that the macroscopic K1 affinity appears to be stronger, right? It's lower, it's smaller, it's 1/2 the true microscopic affinity. While that second macroscopic binding constant appears to be weaker. It's 2 times, it's bigger. Remember, these are dissociation constants, so it's 2 times the true microscopic affinity, right? So this points out two things. One, those macroscopic binding constants are not true binding constants, as we first talked about it. They have these statistical factors associated with them. The second is, so where's that coming from? Well, if you think about it, right, let's take this first one, for example, right? So in the first case, where P could bind, it could bind to either the A side or the B side if we're thinking microscopically here, right? Right, so we could go this way, right? Or this way, right? There are essentially, relative to P, there are 2 ways to bind, right? You got 2 sites. So if you can think about it, the concentration of available sites is, say, 2, right? But if you think about the ways that you could reform from this PA state, the free state, there's only one way to dissociate, right? Because in case PA or on the A side or P on the B side, in either case, a single dissociation event regenerates the completely unliganded form, right? So another, like I said, another way to think about this is that the concentration of free sites is like 2-fold compared to this situation where you have PA, right, to form PA2. If you already have PA formed, whether it's on the A side or on the B side, there's only one way to bind, but there are 2 ways to dissociate, right? Which means the effective concentration of available binding sites right here is lower than it is in the case of the completely unliganded molecule, making the overall affinity, without any sort of consideration of which site is going to bind first, appear to be weaker, right? In terms of the sort of overall amount of A that's bound in solution, right? And the linkage here through these microscopic affinities is simply a statistical consequence of the number of binding sites and how they've been occupied, right? Okay, so that is sort of the linkage between these two different views. And you ultimately, hopefully see that even though you come down to two expressions that on their surface look completely different, they're very closely related. Both of these expressions, a microscopic and the macroscopic expression, will fit data just fine, but the underlying meaning of the numbers is different, right? In the case of the microscopic binding equation, those are the true affinities for the individual sites. Whereas in the macroscopic case, it's sort of the overall sort of apparent affinity, if you want to think about it that way, for binding one site. Doesn't matter which one, but for one of the available sites to be saturated. And there is associated with that a statistical factor. And early in the binding process, those statistical factors make the scale, the true single site affinity, as being apparently tighter because there are more of them. And as you fill it, those macroscopic binding constants relative to that microscopic affinity would then appear to get weaker because of the statistical aspect we just talked about. Okay,